Good afternoon, ladies and gentlemen, and welcome to the session OS Embedded OS Open Source. My name is Matthias Müller. I work at the University of Applied Sciences Leipzig, and I'm very happy to be your session chair for today. As you may know from the time schedule, we now will hear three individual talks, each of a half an hour. And after that, we will have an Q&A at the end. So if you have any questions regarding the talks, please put them into the Slido so that we can go for them afterwards. And don't forget anything. Okay, our first speaker for today is Sergio Prado from Embedded Labworks, a company based in Brazil. And I'm very happy to have him here again. He was also a speaker last year. I had a very, very nice talk. And this time he will talk about the differences in the Android open source and the normal Linux distributions. So please go ahead.
Thanks, Matthias, for the introduction. Yeah, so the talk today is going to be about how an Android operating system based on the Android open source project differs from a Linux distribution like Debian or even a custom built Linux distribution with build-root or Yocto. So I hope that should be useful for people that are starting with an Android on embedded devices and want to learn a little bit about the architecture of Android. And also for those that want to know a little bit about the difference between developing for Linux-based system and Android operating system. Of course, both are based on the same kernel, the Linux kernel, but as we're going to see in this presentation, there are a lot of difference between an Android operating system and a Linux usually operating. So yeah, let's start a little bit about myself. So I've been working with embedded systems for more than 20 years. Currently, I'm working at Toradex. I'm the team lead of a team that develops an operating system for embedded devices that are based on containers. I have also my company here in Brazil, Embedded Labworks, where I've been doing a lot of training and consulting for the last 10+ years. And I've been contributing to a few open source projects like build-root and the Linux kernel. So yeah, let's start. When you think about a Linux operating system, we have basically three major components, right? We have the bootloader, we have the Linux kernel, and we have the root file system, or the user space components, right, with all of our libraries and applications. So if we look at Debian-based system or a custom build system with Yocto, for example, we're gonna have basically the same components, right? And if we look at an Android operating system, yeah, we're gonna have basically the same components. So we're gonna still need one or more bootloaders, depending on the hardware architecture. We're gonna have the Linux kernel there, right? So far, Android is still based on the Linux kernel. But as you're gonna see, it depends on a few extra features from the Linux kernel to boot it. So we're gonna talk a little bit about it. And if we look at the user space component of the Android operating system, then we're gonna see a lot of difference. From the way you build Android to the components used in the operating system, and also the architecture of the operating system, how those components communicate with each other. So we're going to talk a little bit about this in this presentation. So those are the components in a more detailed view, right? We have in the bottom the Linux kernel, and on top of that we have basically three layers: the native layer, the orange blocks, where we have all of the native code that runs outside the Java virtual machine. On top of it, we have what they call the Android framework, basically all of the Java, and today we can also build with Kotlin components, but all of those components will run and will be managed by a Java virtual machine. And on top of it, we have the application. So it's very clear those three major components in the Android operating system. Let's start talking a little bit about the kernel. So Android is built with the kernel Linux, but to run Android, you need a few extra components. Today, it's already integrated in the Linux kernel, so today it's possible to boot an Android system with a kernel if you configure it in the right way. But you need some extra components. We could have a full presentation on what are the changes in the Linux kernel to run Android, but I can mention a few changes. For example, binder. Binder is basically the mechanism to do inter-process communication in Android. So it's an IPC mechanism where one process can send messages to other process, and it is also an RPC mechanism where one process can request an execution of a remote method from other process. We can do a parallel here with dbus, for example, right? But the binder is implemented in kernel space. We have also hashman. That's a kernel component that provides memory allocation for shared memory in Android. So for some reasons, the Google engineers decided to not use the POSIX interface for shared memory allocation. They decided to implement their own mechanism. It's called hashman. We have also another feature called low memory killer that is built on top of the out of memory killer of the Linux kernel. That's the part of the Linux kernel that manages the system when it has low memory. Android decided to, the Google engineers decided to add some logic to the default of memory killer of the Linux kernel, and they call it the low memory killer. So those three are three examples, right? The first two is kind of mandatory to run Android, but there are a lot of other features and changes in Linux kernel that are not mandatory, but would improve a lot the experience on an Android system. If you are building a system with Android, you're gonna probably want those changes. So we're gonna have to get those changes from the kernel common repository from Google and add to your kernel. Going up, we have the user space, and that's where we have most of the changes, right? Let's start with the system in general. So we call AOSP, Android Open Source Project, the full user space implementation of the Android operating system. All of the projects that we have the user space components. Usually, we download those components with a tool called repo. So a repo, it's basically a tool that makes it possible to manage a project that contains several different Git repositories, right? Because for each small component of the operating system, we have a Git repo, and we have a kind of manifest file, XML file that describes all of those repos, and the repo tool is used to manage, to download those and sync those with upstream. So those two commands there, repo init, pointing to the default Android manifest, and repo sync to download those repos, are the basic two commands to download the kernel, the Android source code. And you do that, you're gonna have around, at least for the last Android 11 version, you're gonna have around 100 gigabytes of disk usage. It's really big, the source code of Android. And after the first build, you're gonna double that. So you really need a lot of disk to work with Android. When you list the source code, you're gonna see all of the components, the user space components there, and that differs a little bit, right? When we compare, for example, with build root or Yocto, we don't usually have this kind of vision with all of the source code of the user space components there. We have usually some tarball somewhere, But this kind of vision where it's like looks like a single application, right? But here we have the source code to build the full user space of Android. All of the directories here, for example, system, we have the basic system libraries and command line tools and some daemons from Android. In the frameworks directory, we have basically the implementation of the framework, the system services, the APIs are all here. So yeah, in the end, when you clone the source code with repo, you have all of the source code there in your machine, and you can change anything and rebuild it, and you're gonna have the change right away. The build system. Usually when we work with Linux, we have basically two options, right? Build root and Yocto. Those are the two main options. Google decided to implement a custom build system for Android. They started with simple make files, but after a while they decided to move more manageable build system, and they created their own that they called Song. It's a little bit different from what we know, right, with build root and Yocto. So in build root, we just need to work with make files. With Yocto, we have the bitmake files, and we need to learn how to write those bitmake files as some other metadata. In Android, we have basically a file called blueprint file that is processed by a tool called Blueprint that will generate a Ninja file that will process it by a Ninja tool that will create all of the software artifacts, all of the binaries, libraries, and in the end, the images. Um, as I said earlier, uh, some versions ago, they just supported make files, so there were several Android.mks in the source code of Android, and only that. And you would use purely the make tool to build Android. Um, those files are still there, but they are moving to blueprint files, so you can still see the make files there. But it's a kind of, they are just moving to blueprint files, so probably in a future version we won't have those make files anymore and only blueprint files. Basically, those files describe how to build software, right? It's just another way to describe how to build software. To build Android, you basically have to search on a script, select what you want to build. They call it the product, and then you just build running make. Internally, make will run all of those tools to build the software artifacts and in the end, the images. Usually, when we go to a Linux-based operating system, they are kind of standard, right? You're going to see the same base directories there, /c/var /lib/user, because that's standardized. But as you can see in Android, that's not true. So Android doesn't follow any real standard. They have their own standard. So if you get a shell inside an Android operating system, you're not going to find, for example, /sbin/user/ you're not going to find those directories. You're going to have another directory, for example, there's the /system directory, where you have all of the system binaries, or the /data directory, where you have all of the user data. So it is really different from usual Linux-based operating system. And even if you take a look at the partition layout, it is different. We have different partitions for different purposes. So in Android, we have the system partition. In the past, it was mandatory to have a kind of RAM disk partition, but it's not mandatory anymore. So we have the system partition with all of the system binaries that comes from Google with its generic image. And then we have specific partitions from manufacturers. So for example, we have the vendor partition, where the SoC manufacturer, for example, Qualcomm, can put his own software artifacts there, like libraries, applications. We have the ODM partition where for example, the phone manufacturer would add his code there, his artifacts there. So for example, Motorola, LG, Samsung. We have the product partition where the companies that manage telecom, like the telecom companies, would add his own software artifacts there, libraries and applications. So the idea here is to make it possible to update easily, right? Without messing up with other parts of the system. So as you can see, yeah, Android also differs a lot in terms of the organization of the partitions. And you're going to have much more partitions because, for example, today, if you want to certificate Android, you need to support an A and B update system. So we're going to basically duplicate most of those partitions. Going up, we have the native layer in Android. I'm going to talk a little bit about it. So start with the libraries, right? And Android doesn't use any library that we are used to use in an embedded Linux system, for example, glibc or uclibc or musl. No, we have a specific C library in Android called bionic. I guess they decided to use or to implement this library that as far as I remember, was based on a BSD library. For a few reasons, like license, they really don't like GPL, speed and size. The implementation of Bionic is really simple, but it's good to know that it doesn't support the full POSIX. So what happens sometimes is that you need to adapt your code to run on Android or your native code. So this is just an example from a snippet of code from Busybox, where you have there some if-def Androids adapting the code to run on Android. That's because Android doesn't follow POSIX. So you have some system calls missing, for example, or the behavior of some system calls is not the same as you would expect on a POSIX system. Busybox is another important component in an embedded Linux system, and we would think about that Android also uses Busybox, right? And that's not true. Android doesn't use Busybox. For those who don't know, Busybox is a component that provides all of the major command line tools that you will need in a terminal running Linux. It's very useful. You just install Busybox and you have almost everything that you would need in a Linux terminal. But because of the license, I guess, Android doesn't use Busybox. So in the past, they decided to use a tool called Toolbox. Right now, they are moving to a tool called Toybox. But if we compare those tools, right, the Busybox, we have a lot of different tools. In Android, we have Toolbox with a few tools and Toybox with more tools, but it really doesn't compare to Busybox. Usually when I'm working with an embedded Android system, I just build and install Busybox there because there are really a few tools that is missing. For example, if you want to edit a file inside Android in the terminal, you don't have a text editor by default in Android, like VI or Nano or yeah. And one of the reasons to install Busybox is just to have a VI there so you can edit files directly in the device. Init system. So it's kind of standard today, right? On a Linux system, we use systemd as an init system implementation. On embedded devices, that's not true yet. For example, when you build a system with build root, it will use system5 init based init system. That's the same with Android or with Yocto. So if you build Pocky, it will build a system with system5 init by default. So we would imagine that Android uses systemd or system5 init, right? No, that's not true. Android has its own init system. It doesn't have a name. It's just the Android init system. And it's very different from an init system that we use on Linux. I don't have time here to go to the details. Just can say that it's very different the way the syntax and semantics of the files to configure the init system. But it's nice in a way. It's very nice, but it's just different. So you have to learn it if you want to start, for example, native applications in Android. You're going to have to learn how this init system works. One of the responsibilities of the init system is to load daemons, start daemons, right? Those daemons are processes that will run in the background and will basically manage part of the system, a feature. For example, there are daemons to manage networking. There are daemons to manage the communication with the radio. There are daemons to manage the audio system, and etc. We have a lot of daemons in a Linux system, right? And we would imagine also that Android uses most of those daemons, right? So, for example, we have udev on Linux. That's a daemon that helps to manage device hot plugging, for example. We could imagine that Android also uses udev, but that's not true. Android has its own implementation of hot plug management of devices that call ueventd. And that's the same thing for other daemons. So, for example, we have a few implementations of daemons to manage network in Linux. For example, Network Manager. It's a very popular daemon to manage networking in Linux. But Android doesn't use Network Manager. It has its own daemon for Network Manager. It is called netd. And if you go over all of the daemons in Android, you're going to see that most of those daemons are really custom made for Android. Here I have a listing of some of those daemons. They usually finish the name of the daemon with D, so we can see there a lot of different daemons, but that's not necessary. So, for example, logd. Logd is a daemon that manages, as we can see, logs in Android, but it's not like syslog or rsyslog or the journal D from systemd. It's really a different implementation of log management system. The other component that we have in Android that's really not what we have in Linux, it's a hardware abstraction layer. So in Linux, if we want, for example, to talk to a serial port, we just open a TTY file and write to it, right? That's it. If we, for some kind of interfaces, we can use libraries, right? So if we want to talk to a graphical interface, we can use libgrm and etc. But that is not really this concept of the hardware abstraction layer, right? The kernel with our drivers will abstract the access to hardware and export files, mostly, or network interfaces for network-based devices. And the applications will just use that. In Android, it's a little bit different. So this is a kind of view in Linux, right? We have the hardware and the kernel with drivers that support an interface, and then we have libraries and application using those interfaces. When you go to Android, it's a little bit different. So Android is really a kind of componentized operating system. A lot of components, and each component has its own responsibility. So just as an example, right, we have back there UART interface, T2IS0, for example. So let's say an application wants to write or read from this serial port. It's going to call an API. Usually they call this API manager, so we could have a kind of serial port manager, something like this. The API would send a message to a service, and here we have a kind of inter-process communication using binder. Request the service for this communication. So if the application wants to send a message to the UART, it's going to call a function from this service requesting that. The service will do a lot of things. For example, we check permission. So the service will check, has this application permission to write to the serial port? Because in Android, we have this concept of permission, right? You're going to write your application with a description file, a manifest file describing what you want to do, and the user has to accept that. And the service will check that. And then the service will call a hardware abstraction layer that will abstract the access to the hardware. And the hardware abstraction layer will talk to the hardware. The idea of the hardware abstraction layer is to, as the name implies, abstract, right? So if you change the interface, you doesn't have to change the services. So the services are common code If you change the interface, you change the HAL implementation, and that's it. So basically, what happens is that Google manages all of those codes, those applications, APIs, and services. Those are kind of generic code with generic interfaces, defined interfaces. And also the HAL interface is pretty well defined. And the manufacturer, the vendor, will have to implement all of the HAL to provide the access to that device in an Android system. So all of the HAL implementations will come from the manufacturer or the vendor of the device. On top of that, we have what we call the framework. Basically, all of the code that runs on top of the Java virtual machine. That was Dalvik in the past. Now they call Art. Here we have basically the APIs. That's what the user in the end, when I say user, I mean the developer of the applications, will see, right? And the APIs is basically some kind of abstraction to the services. And the services will do the hard job here to talk, to use the resources of the device. We can list the services in Android with a command service list. We're going to see a lot of services there. And the services expose an interface, a remote interface where we can use via binder. So we can call functions from these interfaces. And again, that's the idea of a system service. Abstract the access, centralize the access, and also do permission checking. So manages the security of that specific resource. That could be a hardware resource or a software resource. For example, power, we have a service for power. We have a service for camera. We have a service for sensors, and go on. You can even call services from the command line in Android. So if you get a shell in Android, you can just, for example, make a phone call, calling the phone service, so service call phone. Here I'm saying I want to call the second method with these parameters. If you can get a shell in Android with ADB, you can just run that. You're going to do a call from the command line. In the end, we have also the application layer, and basically the application is what we see in the end, right? And that's one of the advantages of using Android. We have a very nice and cool API with very nice tools to use. So in the past, it was just Java-based API. Now we can also write applications in Kotlin. And the applications are packaged in a file called APK. It's basically a zip file with the components there. So that's also a little bit different from a Linux-based system, right? Of course, you could package your application with some package manager like Tab or Flatpak or anything else, but in Android, there is this specific format called APK. So yeah, some conclusions from this talk. As we could see, there are a lot of differences in an Android system comparing to a usual Linux-based system. The only similarity I would say is that they are both based on the Linux kernel. But as we could see, Android needs some special or extra features in the Linux kernel to run. And everything else is almost different, right? From the way the source code is organized, from the way it is built, from the organization of the file system, from the way the components of the user space communicate with itself, from the way you write and deploy applications, everything else is different. So I would say, personally would say that Android is not a Linux distribution in a sense that's really a different beast. But if we define a Linux distribution as an operating system that uses Linux, then we could say that Android is a Linux distribution. But if we say that a Linux distribution is a system that has kind of similar components and structure of other Linux distributions, then we cannot say that Android is a Linux distribution. I hope you guys enjoyed this presentation, and I'm looking forward to questions in the end of this session. Thank you.